Hello favorite students and welcome to the video Solving Force Problems on Ramps. We're going to be using the same process that we used for solving force problems before, but now you'll notice instead of being on a flat ground, we've taken our ground and we've turned it, so we've got a ramp. So I am on page 21 of your notes pack. You can see here I've got a ramp and I've got a mass just like you have, and I have an angle. What I'm going to do is I'm going to show us how to solve this problem. So it says on page 21, and for reference, again, here I'm on this problem, that the first thing we need to do is to choose an axis. So in all of our previous problems, we always had x going flat and y going straight up and down. But what we need is we need to draw our axis so that it points in the direction of the acceleration. So I'm actually going to draw my x-axis like that, and my y-axis like that. So I've got my x-axis that is parallel to the ramp, and my y-axis perpendicular to the ramp. In the same way that when we had a box, just a normal box, on flat ground, we had x and y, and x was parallel and y came straight out. We're doing the same thing here, right? If I took my ramp and I turned it like this, I can see here's my ground, my x-axis, and my y-axis going straight up. So it's the same idea. We've just taken everything and we've turned it a little bit. So now we're going to draw our free body diagram. So I'm actually going to show my forces right here on the board. I've got force of gravity. Now, even though we have turned our axis, gravity still goes straight down. And normal force always comes straight out of the surface, perpendicular to the surface. It might be tempting to draw the normal force like this because we are used to the normal force coming straight up, but that is not correct. The correct way to draw it is the normal force coming straight out of the surface, 90 degrees to the surface. So when I draw my free body diagram, I'm going to make that just a little bit shorter. When I draw my free body diagram, I'm going to put my dot. I'm also going to put my x and y axis on my free body diagram to help me keep track. X and y. And what I'm going to do is I know that normal force comes straight in the y direction, Fn, and gravity comes straight down, Fg. And what I can see is now gravity, where it used to be in the y direction, now it's at an angle. And so I have to use SOHCAHTOA to break it into its parts. So I'm going to come back and look up here, and I see that this is the angle of my ramp. For you geometry people, you'll know that all of the angles have to add up to 90. So let's say that this angle here was 90, and we made our angle here 30. And all of those have to add up to 180, which means this angle has to be 60. Now, if we continued our y-axis down and made a new triangle, we would know that this angle here would have to be 30. And we see that this angle and this angle are the same. So we can go to our free body diagram, and between gravity and the y-axis, we can always make this the same angle as the ramp. So that is something that you can think through every time, or you can just memorize between FG and FGY is always the same as the ramp. Always the same as the ramp. So now what I can do is break this into FGY and FGX. And the FGY is the part of gravity that kind of pulls it into the ramp. And the FGX is the part of gravity that pulls it down the ramp. So the FGY is actually what creates my normal force. The FGY creates my normal force, and the FGX is what causes me to accelerate down the ramp. So when I then move on to my Newton's second law equations, and I see that F net y equals 0, and I have normal force minus, not Fg, that's not in the y direction, specifically Fgy, the y component, Fgy is equal to 0. And then I know that this Fgy is the adjacent side of this triangle, and so that changes into Fg cosine of theta equal to 0. And if I add that to the other side, the normal force is equal to Fg cosine theta, or the mass times little g times the cosine theta. So we can see normal force in this case is not equal to gravity. It's equal to the y component of gravity. Because if I take my axis and I turn it, I can see that my y component and my normal force are equal, but gravity is still much bigger. So I need to do SOHCAHTOA, and I see that my normal force is equal to mg cosine theta. If I do the x direction, and we'll do it up here, F net x equals ma. The only force I have going in my x direction, if I turn and look, is this component of gravity here. That is pointing in the x direction. This is my positive x direction. So that means that Fgx is equal to ma, which also means that mg sine theta is equal to ma. And then I see that I have an m on both sides, so I can divide both sides by m, and I will find that the acceleration is equal to g sine theta. So ramps are kind of tricky. We have to turn things at an angle. We have to use SOHCAHTOA on our gravitational force to find the y component and the x component, but the same general idea is the same. Move that a little closer. The same general idea is the same. We draw the free body diagram. We split up anything that's at an angle, which in this case is gravity, and then we use our F net x and our F net y to solve the problem. We just have to remember that in this case, x is no longer flat, it's down the ramp. X is down the ramp, and Y is out of the ramp. Out of the ramp. So if you ever get stuck, just remember we've just got the same as the flat ground, and we've turned it. I hope that was helpful. I know we're still going to need to cover some more in class, so we're going to get some practice, but please do your best on the practice problems, and we will go over it in class next week. Be the leaders your community needs and deserves, choose to be great, and make your dreams come true.